Dear students, today we will be discussing about a tutorial on solar concentrating collectors. Okay? So, this tutorial goes something like this. We need to calculate heat removal factor, the useful heat gain, the exit fluid temperature and the collection efficiency for a cylindrical parabolic concentrator having 3 meter width and 10 meter long. The outside diameter of the absorber tube being 7 centimeter, and that has to be calculated on 15th April at 12 hours 30 minute local apparent time. Consider the latitude and slope as 19.12 degree and 9.625 degree respectively. The temperature of the fluid to be heated at the inlet is 160 degrees C with flow rate of 480 kg per hour. The incident beam radiation is 750 watt per meter square. The ambient temperature is 27 degrees C and optical properties are also given. So, this rho, which is nothing but specular reflectivity of the concentrator surface, okay, and this tau alpha multiplication for beam radiation is given to be 0.78, and gamma, which is nothing but intercept factor. So, this is intercept factor, okay, which is equal to 0.93. So, what is intercept factor? The fraction of the reflected radiation intercepted by the absorber tube, right? And rho, what I said before, is specular reflectivity. Of concentrator surface, okay, and for 15th of April n is equal to 105, okay, and phi is given as 19.12 degree and beta, which is nothing but slope, which is given as 9.625 degree, and omega, because this is 12:30 hours, that means 1 hour means 15 degree, 1 hour is 15 degree and half an hour is 7.5 degree, but since it is afternoon, so we will use negative sign, right. So, omega is minus 7.5 degree, which is nothing but hour angle. Okay. So, if we know n, then from that we can calculate what is delta or declination. So, we know the expression for declination, which is nothing but 23.45 sine of 360 divided by 365 284 plus n. Okay. So, if we substitute the value of n, which is equal to 105, then this delta or declination is found to be 9.415 degree. Okay. So, declination is known. So, we know now phi, then beta slope, then hour angle and declination. Okay. So, now what is next? We need to calculate till factor, okay, because we need to find out the absorbed solar flux. Okay. So, before we initiate the calculation, let us draw the figure first, that means cross section of a cylindrical parabolic collector, right. So, if you consider this is the tube and this is the glass cover, okay, and concentrator is something like this, okay. Can extend this somewhat and can draw this. This is nothing but a concentrator, okay. Solar radiation is falling here and it is going here, falling here, and is reflected to this absorber, and maybe I will name it as this may be 1, this may be 2, and this may be 3, okay. And we can draw this here, and maybe I can draw here and here. So, this part is W, okay, which is nothing but the width, and length is towards this, okay. It will go something like this. So, here 1 is nothing but absorber tube, then 2 is nothing but the glass cover, and 3 is concentrator, okay. And also we can see how this fluid flows, okay. So, fluid is flowing inside the tube, okay. So, Tf I may be the inlet fluid temperature, okay. So, that way we can do it, okay. So, fluid is flowing through this tube, okay. So, maybe Tf one things and then Tfo in the other side, right. So, here W is the aperture and length is L, and also we can define this rim angle if required. This is the rim angle, which is nothing but phi over r, okay. And inlet fluid temperature is Tfi, outlet fluid temperature is Tfo, and if we consider a fluid having specific heat is Cp, is the specific heat of the fluid. Now, we need to find out the till factor, because if we write the expression for absorbed solar flux, that means the amount of solar radiation which is absorbed in the absorber tube, okay. So, this is the absorber tube and this is the glass cover and this is the reflector. Solar radiation is falling on this reflector and it is reflected back to this absorber. Again, some component of radiation is falling directly on this absorber through this glass cover, okay. So, we have done the entire derivation. Now, we are interested about the absorbed solar flux, which is represented by S, okay. So, we can write IB, then we have RB, then we know rho, then gamma, tau alpha for beam radiation, then we have IB, then RB, tau alpha for beam radiation, then D naught divided by W minus D naught, okay. So, this is the expression by which you can calculate the absorbed solar flux in the absorber, okay. Now, these values are known, IB is known, rho, and then intercept factor tau alpha for beam radiation, okay. Beam radiation D naught, W, D naught, everything is known except RB, which is common in both the parts of this expression, okay. Now, let us calculate what is RB. RB is nothing but the till factor for beam radiation, which is defined as the ratio of the beam radiation flux falling on the tilted surface to the radiation falling on a horizontal surface. Okay. So, this is something like we have cos theta to cos of theta z, right. So, if we write the expression for this will be something like sin delta sin phi minus beta plus cos of delta cos of omega multiplied by cos of phi minus beta, okay, to the sin of delta sin of phi plus cos of delta cos of omega cos of phi. Okay. So, we know the values of delta, phi, beta, omega. Okay. So, if we substitute here, then what we will get? So, let us substitute. So, sin delta is 9.415, then sin phi minus beta, phi is 19.12 minus beta is 9.625. Okay. Then we have cos of delta, delta is 9.415, and then we have cos of minus 7.5, then we will have cos of phi is 19.12 minus 9.625. Okay. And then we have sin delta is 9.415, then sin of phi is 19.12 plus cos of delta is 9.415, then we have cos minus 7.5, then we have cos phi is 19.12. Okay. So, if we do the calculation, then this RB is found to be 1.0142. Okay. So, this is nothing but RB. Okay. So, this value is known now, then we will use this value of RB in the expression 1, okay, which is nothing but absorbed solar flux. Okay. So, use the equation 1. Equation 1 implies we will have S is equal to, already we know IB, which is given as 750 multiplied by we have RB, which is nothing but 1.0142 multiplied by we have rho, it was 0.85, then multiplied by tau alpha average, which is nothing but 0.93, then we will have intercept factor. So, let me see what are the values there. So, tau alpha average is 0.78 and intercept factor is 0.93. Okay. So, this is gamma and average is 0.78, it is same, it is a multiplicative only. This plus we will have another expression 750 multiplied by RB 1.0142, and then we will have 0.78, and then we have D naught. D naught is 7 centimeter, which is equal to 0.07, and we have W is 3 meter divided by 0.07. Okay. So, if we do the calculation, this S is found to be 483.184 watt per meter square. Okay. So, this is the flux received, right. So, once we know this S, then other parameters can be calculated, like instantaneous efficiency and QU. Okay. So, for that again we need to calculate one parameter called heat removal factor. Okay. So, how to calculate this heat removal factor? So, heat removal factor Fr, it is normally represented by Fr. So, this is the expression m dot Cp to the pi outer diameter L, then you have UL, which is nothing but overall loss coefficient, 1 minus exponential of something like we will have minus F dash, which is efficiency factor for the collector, D naught, UL, then we will have multiplied by L, and m dot Cp. Okay. Right. So, this m dot, what is given here? So, m dot I will write here is given as 480 kg per hour. So, we need to convert it to kg per second. So, 480 divided by 3600, which will give kg per second, and if we simplify it, so it will be 0.133 kg per second. Okay. This is m dot, right. So, here we have to use this kg per second. Maybe we can write this as equation 2, okay, and we can calculate this term. Okay. So, this term, because this term is common here also. Okay. So, once we calculate, then it will not be so complex. Okay. So, this term m dot Cp divided by pi d naught L UL, okay, which is equal to 0.133, and then Cp value is given as 1.256 into 10 to the power cube. Okay. Then pi multiplied by d naught is given as 7 centimeter. So, it will be 0.07 meter, and then length is 10 meter, and UL is given as 7. Okay. So, this result will be 10.85. Okay. So, this value is found to be 10.85, right. So, now if we use equation 2, what will happen is Fr will be equal to 10.85 multiplied by 1 minus exponential of 1 minus, it will be f dash divided by 10.85, right. So, it becomes very easy to calculate now. So, this Fr value, if we substitute f dash which is given as 0.85. Okay. So, if you substitute, then Fr is found to be 0.817. Okay. So, Fr is found to be 0.817, right. So, in the next calculation, we need to find out Qu. So, let us write down the expression for useful heat gain. Useful heat gain Qu, which is equal to Fr W minus D naught into L multiplied by S minus UL by C, which is nothing but concentration ratio. So, we need to find out the concentration ratio now, TFI minus TA, as we know the other parameter, right. So, Fr we have calculated and only unknown is C here. Okay. So, how to calculate C? So, let it be equation 3, and C is nothing but concentration ratio, okay, which is defined as effective aperture area, to the absorber tube area. Okay. So, this is nothing but W minus D naught, then we need to multiply with L, okay, and we will have pi D naught into L. Okay. So, L will go from numerator and denominator, then resultant equation will be W minus D naught by pi into D naught. Okay. So, we know the value of W and D naught. So, if we substitute here, then what we will get is 3 minus 0.07, and here pi value 3.14, and we will have 0.07. Okay. So, final value of C will be about 13.32. Okay. So, we know now concentration ratio values for this configuration, which is about 13.32, right. So, let us calculate the useful heat gain. So, this is Qu, or we can write here equation 3 implies Qu is equal to Fr value, Fr is known to us, which is 0.817, then W is 3 minus 0.07 is the D naught, and L is 10, right. Then this has to be multiplied by this parameter. So, S, which is calculated to be 483.184 minus UL is 7 and C is 13.32, then TFI is 160 and we know TA is 27. Okay. So, if we do the calculation, this Qe is found to be 9893.35 watt. Okay. Qe, right. So, once we know Qe, then from that we can calculate what will be the instantaneous efficiency, right. So, how to calculate this? So, we know Q is equal to m dot Cp then Tfi minus Tfo. Okay. So, this may be equation 4. Okay. So, once we substitute the value of Q here, then from that we can calculate what will be the value of Tfo, right. So, Q value is 9893.35 and then mass flow rate is 0.133 multiplied by Cp is 1.256 into 10 to the power of 3 and Tfo we need to calculate. So, this expression we have to reverse it. Okay. So, Tfo by Tfi. Okay. So, it will be Tfo minus 160. Okay. So, from here we can calculate what is Tfo. So, which is found to be 219.22 degree C. Okay. So, we have calculated what is Tfo, right. Now, what we need to calculate is the instantaneous efficiency. Okay. Instantaneous efficiency eta I, which can be expressed Q by IB RB W into L multiplied by 100%. Okay. So, this Q we have calculated and it is found to be 9893.35 and IB is 750 multiplied by 1.0142 for RB and W is 3 and L is 10 multiplied by 100%. Okay. So, if we do the calculation, it is found to be 43.35%. Okay. So, for this configuration, this instantaneous efficiency is calculated to be 43.35%. Okay. So, what are the parameters we have calculated? First, we have calculated S value. So, S was calculated to be 483.184 watt per meter square. Then we have calculated Fr. So, this Fr was found to be 0.817 and then we have calculated concentration ratio which was 13.32 and then we have calculated useful heat gain which was found to be 9893.35 watt. Okay. And after calculation of this, we have used the expression Q is equal to m dot Cp Tfo minus Tfi. Okay. So, based on these calculations, what we have calculated Tfo, which is found to be 219.22 degree C. And finally, we have calculated instantaneous efficiency eta I, which is found to be 43.35%. 1%. Okay. So, in this problem we have demonstrated how this solar absorbed flux can be calculated, then how to calculate QU. For calculation of QU we need the value of Fr and F dash. So, Fr is nothing but heat removal factor and then F dash is efficiency factor of the collector. So, once we know this, then we can calculate what is QU. Of course, we need to calculate concentration ratio. Then after that we can calculate TFO and instantaneous efficiency. Okay. So, this kind of problems are very practical, and I hope you have enjoyed this video, and hopefully you are now capable to design a solar concentrated collector. So, thank you very much.